Yeah, before I start, I'd like to thank Subrat and Oga for inviting me to talk here. I'm very happy to talk about this work. But I must warn you, it's all very elementary. What I'm talking about is probably the most elementary talk in this whole, of all the talks that we've heard so far. And I hope that will be received in the right spirit, because it's good to have elementary talks because then everybody understands them. So what I'm going to talk about is gravity and decoherence. This is actually a very old topic which has been around for a long time. And I felt I wanted to revisit this topic. And I'll just tell you the outline of the talk before I start. So first I'll talk about gravity and quantum theory. Second is gravity and decoherence. Then I'm going to talk entirely within the paradigm of the two-slit experiment and propose two variations of the experiment which and I call them E1 and E2, two experiments, just to distinguish between them. And these experiments can be analyzed both physically and mathematically. So first I will talk about the experiments from a physical point of view, and then produce a mathematical argument, which is actually quite easy, to finally conclude that gravity does have something to do with decoherence. In other words, that gravity has the effect of undermining quantum mechanics in a certain sense of the term. So everyone in this room is here because they're interested in the relation between gravity and quantum theory. And these are two theories, each of which has been quite successful in its own domain of operation. So what is the relation between these two theories? That's a question that everyone is interested in. And a lot of work has been done in this to try to fit these two things together. If you think of it as a jigsaw puzzle, here are two pieces of a bigger puzzle. We'd like to know how they fit together. And it's already clear that there is tension between these two theories, and whenever there's tension, you can hope for some new insights to come. So when you have a jigsaw puzzle, as everybody knows, when you try to fit the pieces together, you use everything you know about the puzzle. For example, if there's the same color of pieces, you think they might be together in the same tree or something. And if you see a corner piece or an edge piece, you use all that information. So what has been primarily done in this area is to look at quantum gravity. And this is the study of quantum gravity usually entails the study of new theories which agree with GR at low energies. So here one is investigating the high energy behavior of gravitation. How does gravity behave at small distances? That's the domain of quantum gravity. Normally we think of gravity whenever we talk about large objects like the solar system or planets, and we think about quantum mechanics when we're thinking about tiny objects which are found in accelerators. Now, apart from quantum gravity, which explores the short distance behavior of gravity, we would also like to explore the large distance behavior of quantum systems. And there probably is no good name for it, but let's call it gravitational quantum physics. So the trouble with quantum gravity is that, well, when one is exploring new theories, our accelerators are not much good. One has to use primarily theoretical ideas, and there's very little experimental guidance. So that is one approach which is being tried quite seriously, including string theory and all the efforts in that direction. Another approach is to just understand the theories we already have. Take quantum field theory, which we understand, at least quantum electrodynamics we understand, and then take the classical general relativity, and put these two theories together by thought experiments and try to push each to the limit and make them confront each other, create a problem that we would have to resolve. That's the philosophy I'd like to follow. So there's been a very old, okay, perhaps I should say one more thing before going on. So we were talking about pieces of a puzzle. We have general relativity, and we have quantum theory. And we are asking how they fit together. I think one point which is already clear is that there is a third piece of the puzzle, and that is statistical mechanics. And definitely, when you put these two together, you automatically get statistical mechanics. And this has been known for a long time, from the time of Hawking's work on Hawking radiation, that these two pieces are insufficient. Once you put in quantum mechanics plus GR together, you end up with this. And in support of this claim, I would like to point out that about 50% of the talks at the Strings meeting were on statistical mechanics. So the importance of thermal physics, entropy, and statistical mechanics is well recognized in the community. So it's clear that it's not just these two things that we're putting together, but that is also part of the whole equation. Now, there's been a very old idea that Penrose put forward, and actually, not Penrose, it was really Feynman who put it forward in Chapel Hill. Diosi put it forward, I think, independently, and Penrose has been propagating the idea for a long time that gravity spoils quantum coherence. So, in Chapel Hill, there was a conference in 1957, a long time ago, and actually that conference marks the beginning of general relativity re-entering physics. Before that, after the initial excitement about GR in the early part of last century, GR was exiled to the mathematics departments, where people were roughly interested in the differential equations that came out of GR, and not so much in the physical ideas. With this conference, GR re-entered the mainstream, and in the next decade, there was discovery of radio sources and black holes and all kinds of things that made it clear that GR was physics and not mathematics. So in the conference proceedings, you can find this quote of Feynman's. I would like to suggest that it's possible that quantum mechanics fails at large distances and for large objects. It is not inconsistent with what we know. It is this failure of if this failure of quantum mechanics is connected with gravity, we might speculatively expect this to happen for masses such that gmc squared is equal to 1, or near the Planck mass. In gram units, it's 10 to the minus 5. This is Feynman in 1957. And this is basically the force that drives most of this talk. Now, after Diosi and Penrose, there have been many studies of models that try to implement this idea that there's actually decoherence coming from gravity. Now, what I find dissatisfying about all these approaches is that they all use Newtonian gravity, not relativistic gravity, and they use physics which is new in the sense that they postulate or they put in by hand some new physics. For example, there's a model by Rimini, Weber, and Girardi where they say, apart from Schrödinger evolution, which is governed by unitary evolution, there are occasional flashes of spontaneous collapse. And all that stuff means new physics, and unless you have some experimental support for that, it's not really something we would accept. I mean, I find it dissatisfying, so I will just ignore all previous work on this subject. That is one approach also, yes. But these people have stochastic processes. Even a nonlinear term in the Schrödinger equation would probably be time reversal invariant. Yeah, but they have stochastic processes. They actually explicitly put in the collapse. Now, if you look at the double slit experiment, it's something which is taught in bachelor's courses, and Feynman has somewhere said that it contains the only mystery of quantum physics. So you have, never mind these red lines and these blue lines, you have a source here and a detector placed along here, and an electron can get from the source to the detector in two paths. Actually, there are two bundles of paths, but for the moment, let's assume they're just two paths. And you can put on you can open the slits one by one. You can measure the probability of arrival at a given spot when one of the slits is open or the other slit is open, and both of them are open. Now, you find because of interference that P12, which is when both slits are open, is not the same as P1 plus P2. And this goes against our intuition that probabilities of exclusive events add. That intuition is derived from the classical world. And you can also notice that when you have a separation D between the two slits, there's an effective transverse momentum which is of the order of h bar over d. And that transverse momentum is given to these particles, and that is the momentum that's responsible for these fringes. All this is very elementary, and you all know this. I'm just reminding you. Now, that is the two-slit experiment. What I'm going to propose is two variations on the two-slit experiment. First, consider the same experiment. And in E1, these are the two variations of the double slit experiment. In E1, I'm going to put this whole apparatus inside a thermal bath and heat the laboratory at a temperature T. And this is a problem in standard physics, which is easy to solve. In fact, both these are easy to solve. And in E2, I do the whole experiment in mid space, but in an accelerated frame of reference. So the experiment is being done by a Rindler Observer. And see from this, combination of these two experiments, that we will actually draw the conclusion that gravity does decohere quantum mechanics. Now, the reason for formulating everything in terms of thought experiments is that gravity is difficult, because in gravity you have a lot of complications coming from the fact that many effects are gauge. It's hard to distinguish between gauge and reality. And one way of getting around this is to actually concretize everything by formulating a thought experiment. And actually both these experiments are thought experiments, but the first one is actually something you can do in a laboratory if you wanted to. But I'm working at the level of thought experiments, so we just formulate it so that there is conceptual clarity about what we are doing.
The second one has already been done, no?
Is it?
On diffraction experiment. When they do it with gravitational field, that's not the same as axial.
Yeah, let me come to that at the end of it. Yeah, thanks.
Also, is this a test of gravity, or is it a test of, I think if you're going where I think you're going, it's going to, you need also principle of equivalence to talk about gravity.
Yes, that's right. Yeah, that will also come. But let me also say that I'm treating gravity as an external field. I'm not talking about the gravitational dynamics. So there's a fixed background space-time. And what I'm talking about is what happens in that background space-time for large quantum systems. For small quantum systems, I recover the effects that everybody is familiar with. Okay, so let's take E1 first. It's a double slit experiment in the thermal environment, or E2, double slit in an accelerated frame. I'll analyze both these experiments using only known physics. And in E1, I find that thermal fluctuations of the electromagnetic field cause decoherence in the double slit experiment, the electron experiment. And this is very easy to understand. I'll give you physical arguments for that. In E2, what we find is that I'm talking about Minkowski space in a vacuum state, so there are no photons as far as inertial observer is concerned. But these same vacuum fluctuations of the inertial observer appear to the Rindler Observer as thermal. And the Rindler Observer is basically the uniformly accelerated observer, and he sees loss of coherence in the double slit experiment. And loss of coherence, I should quantify it. What I mean by loss of coherence, I'd like to include two things. One is visibility is reduced. Visibility of the fringes is reduced. And the second point is that it is something irreversible. Now, these points are very important. We'll come back to them later. Irreversible, that is to say, there should be information loss. So the analysis can be done both physically as well as mathematically. The physical argument is very simple. Suppose I have a double slit experiment here. Let's go back to this picture. So this red line is supposed to represent a long wavelength red photon, which is hanging around in the apparatus. And this blue photon here is a large momentum photon. So you can imagine that when the electron is going along this path, it will scatter off the ambient blackbody radiation. And if there is enough momentum in the photons, it will destroy the interference pattern. So the red photons will not do very much because the wavelength is too large and the momentum is too little. But the blue photons have enough momentum to kick some electron which would have landed in a bright fringe to kick it into a dark fringe. So you get a washing out of the interference pattern. Physical argument. Now, another way of saying the same thing is that if I look at the thermal electromagnetic field, all correlators have a kind of dependence which looks like this. If I take 2 points, x and x prime, and take the electric field correlation, for example, it decays as e to the x minus x prime upon the Wien wavelength, which is given by this formula. So what that means is that if the temperature is very low, the Wien wavelength is very large, and the same fluctuations appear on top of both the slits, and there's no destruction of the interference pattern. On the other hand, if the Wien wavelength is small, I get different and independent fluctuations over the two slits, and that's what destroys the interference pattern. So this is a picture of a Rindler Observer. This is Minkowski space, and I've kept all the C's and H bars and all that most of the time. This is CT, and this is Z. And these are the light cones. And the red lines show the motion of Rindler observers who are uniformly accelerating. The coordinate transformation from Minkowski space to the Rindler frame is very much like the coordinate transformation from Cartesian coordinates to polar coordinates, except that everything is hyperbolic instead of being trigonometric. So what I imagine is that this guy, he has Z, X, T, Y, Z of his own, which I'll denote by capital letters. In his frame, he does a double slit experiment. So the double slit is at rest in his frame. Now, let me get to the mathematical argument. I'm sorry. I'm sorry?
Are the slits also accelerating?
The slits are at rest in the accelerating observer's frame, which means that they're accelerating with respect to the inertial observer.
And the screen?
Everything. The whole apparatus. Yeah. So this guy, he works in his own rest frame. Another thing I do is that I make sure that everything is stationary. That is to say that I should have been a little clearer about this. See, in this experiment, I forgot two important points. One was that the electrons which are being sent in from here are monoenergetic, so the whole situation is stationary. And also, they don't have too much energy. If you have a lot of energy, that is to say, if the electron motion is relativistic, you can have Klein paradoxes resulting from scattering of these potentials. And that will generate more electrons, more confusion. I want to avoid all that. Work in the regime where the electrons are moving slowly, or if there's a temperature, T is much smaller than mc squared, and let's say that T is comparable to this Wien wavelength. I mean, comparable to D. The Wien wavelength is comparable to D.
Been emitted from the gun. This kind of experiment, in fact, when we do on the Earth, every time in a sense is happening.
Yes.
The electrons, we are all in accelerating frame.
Right, right.
But the electrons then might just follow a geodesic.
So suppose you have a waveguide that takes electrons from here to there.
So there'll have to be something, some electric field or something which also acts on the electrons and forces them to accelerate.
Yes, yeah. You can, just as with optics, you can use a fiber optic tube to guide the photons. You can have a waveguide to guide the electrons along any path you want, along path gamma 1 or gamma 2. Yeah. Okay, here's the mathematical argument. Suppose without another point I should have said is that I'm assuming that the two slits are symmetrical so that the amplitude to arrive is the same, and the visibility would actually be 1. So if I take two symmetrical slits, the interference term, this is the term that causes the fringes. This is the interference term, and the visibility is unity. You can work out the visibility from this expression and standard expressions, and you find that you get perfect visibility in the absence of an electromagnetic field. But now suppose I turn on the electromagnetic field. Each of these amplitudes is modified to this extent. There's a phase factor which comes roughly from this Wilson, well, this is an open Wilson line. And when you put everything together, you find that the interference term picks up a Wilson line which is a closed loop. And that closed loop consists of going along this loop and coming back along that loop. So there's a closed Wilson line which makes perfect gauge invariant sense. And that's the quantity that determines the visibility. So the visibility goes, the interference term goes from I to the expectation value of this Wilson loop in a thermal gravitational field. And that's what we have to work out. Now that's very easy to work out. And you can work it out with exactly the same arguments, whether you're talking about the two-slit experiment in a thermal bath or the two-slit experiment in an accelerated frame. All the changes is that the modes are slightly different. Instead of using e to the power of ikx as the modes, with also polarization degrees of freedom thrown in, you use slightly different modes and use exactly the same algebra. So what you do is you take the vector potential and expand it out in terms of modes. These use, L is a mode sum. And L actually corresponds to, L is equal to K vector and the polarization, if you're talking about Minkowski observer. And it's something more complicated. There's an omega and there's a transverse K and also a polarization if you're talking about the Rindler observer. So you do this mode expansion of A in terms of these modes, which are just, for the moment, think of them as just e to the power of ikx. And these are the creation and destruction operators for the corresponding mode. And essentially, I'm working in the one electron sector of QED. That's what that's where the action is. So you find that W is actually a product over all modes of exponential of this combination, where this alpha is the form factor of the loop. It is just the modes of the electromagnetic field integrated over the loop. It's like it's just the shape of the loop can be arbitrary, but whatever the shape is, you can work out the form factor. And it's some complex number because these are all complex functions. You compute the thermal average, which is actually quite easy. It involves simple manipulations of A's and A diagrams, which I can reproduce if there are questions. And then you find that the the thermal average is given by the product over modes becomes a sum in the exponential. And here you have the fine structure constant, E squared upon H bar C, e to the minus fine structure constant by 2. And then the form factor appears here, and you have this factor. And these factors are very common when you do statistical mechanics of operators. In fact, they appeared in a talk by Amin Nizam earlier. Yeah, such a factor was exactly there also. And such factors also appear in things like the fluctuation dissipation theorem. And in fact, what we are talking about is something like the fluctuation dissipation theorem, because there are fluctuations in the thermal electromagnetic field which are causing kind of dissipation in the loss of coherence. For E2, we find exactly the same mode functions. You find the same expression. Only thing is that these are different. The form factors are different because the modes are different. And if you are in Rindler, the temperature is effectively the acceleration multiplied by all these fundamental constants. And this is a miserably small number. If you actually plug in the numbers, you'll find that the effects are extremely tiny. But that's not the point. As a matter of principle, gravity is causing decoherence. If you go to large enough gravitational fields, you find that this temperature can be considerable and can cause real physical effects.
Sum over L is conversion.
Yeah. Actually, that's a subtle point. There are two subtle points which maybe turn to that point. There are vacuum effects which have to be subtracted out. There's a divergent, but you can make sense of the whole thing. So here's the fringe visibility as a function of the size of D is the separation between the two slits, and T is the temperature. And it has been fixed to be 1 at 0 temperature. I've removed the vacuum effects. And then this is the fringe visibility dying out with the size of the apparatus. And this is for two different curves. This one is for an electron, and this one is for a triply charged ion. Because the fluctuation effects go as the square of the charge, if I take a triply charged ion and try to do an experiment with ions in the laboratory, I'll find that larger charges lead to more rapid decoherence. Anyway, this explicit form is something that one could check by doing laboratory experiments.
These accelerations are quite high.
No. In the first experiment, I don't need accelerations.
No, but I'm saying the second one.
In the second one, the accelerations have to be really high to get any effect. But if you're talking fundamental physics, it's a matter of principle. Is there decoherence or is there not?
But I'm saying that, has there ever been gravity tested in such acceleration?
No, I'm pretty sure not. No. See, the highest fields we know of are near neutron stars, which are like, the Wien wavelength is about 3 kilometers, which is very large. Yeah.
We don't really need gravity, right? We could just turn on a very strong electric field.
That is true.
And do this, and you would get whatever acceleration you like.
That's right.
Accelerations and you
Yeah.
It seems to me there's a classical effect, which is the classical effect of the radiation reaction of the electrons, which is stronger than this effect, I might have thought. I mean, just the fact that the electrons, when they're accelerating, will radiate.
See,
And that might be much stronger than the usual.
can you ask the question just a few minutes later? Yeah, the same one. Yeah. So I'll just finish up very rapidly and then I'll take the question. So conclusion is that I can present a simple model for gravity-induced decoherence. What you need is the Einstein equivalence principle to relate the acceleration to gravity. And when there was a question asked about gravity, I was talking about actual gravity, but you're right, you can also simulate gravity with acceleration using electric fields. And very high electric fields are possible these days with lasers and all that. Now, this is entirely consonant with Feynman, Penrose, and Diosi. They expect similar decoherence effects for static observers. I mean, for example, it's entirely consistent with what these people expected, except that what I'm talking about here is a purely relativistic theory. Unfortunately, when we say quantum mechanics, everybody thinks of non-relativistic quantum mechanics, which is a shadow of the real theory. The real theory is quantum field theory. There's no such thing as relativistic quantum mechanics, and what we have to do is relativistic quantum field theory. Now, I can expect, this was done in flat space, but I can expect similar decoherence effects for static observers outside the event horizon of a black hole too. There are other models of decoherence. I find these unsatisfactory, but I won't take the time to criticize them here. They don't satisfy the second condition. They're not irreversible phenomena. They have experiments where you can do an experiment in a gravitational field and you apparently lose coherence, but you can regain coherence by simply reversing the sign of the electric field. So that's not an irreversible effect. And let me revisit these 2 points. Yeah, this is one of the fine points. The parts that I follow are actually bundles of parts, not single parts, and you have to take that into account when you talk about vacuum effects. And finally, if I replace electromagnetic fields with gravity, I find that the similar effects happen also with gravity. You can have, suppose you have a thermal bath of gravitons, that will cause decoherence of neutral systems in the same way that electromagnetism decohes charged systems. And actually, if you do an experiment with neutron scattering, with neutron diffraction, neutrons do have a magnetic moment and they couple to electromagnetic fields. So you would get a slightly different answer, but it's also a calculable effect. Probably that's one place one could look for it. And gravity decohes quantum systems, and the effect is larger for larger systems. We've seen that before. And it's larger for strongly coupled systems. Now, we should probably go back a little bit and think about what the different attitudes would be towards the loss of coherence. For example, in the thermal experiment, when you have the double slit experiment, so I can take 2 points of view. What's really happening physically and mathematically is that the electrons are interacting with soft photons and information is being carried away by soft photons. So that's the information loss. Yeah? So you can have 2 attitudes towards this. One, in order to get to these 2 attitudes, I'll call the 2 guys Simplicio and Sagaccio. These are 2 gentlemen who were introduced by Galileo when talking about his system of the world. Now, he also had a 3rd guy called Sagredo, who was representing the church. And he put all the foolish opinions in the mouth of Sagredo. But over the years, Sagredo has lost relevance. Roman Catholic Church has lost relevance to all of us. Simplicio is the guy who just does the experiment and looks at what he sees. He says the information is going off in soft photons. I don't know anything about soft photons. I'm a simple guy, I want to get on with my life, so I know that there's loss of coherence. Whereas Sagaccio has a more fundamental approach. He says there was a thermal state of the electromagnetic field, which was thermal, and then that was tensored with a state of the electron field. I'll write rho electron. That was pure to start with. And this went to a state in which there was impurity in both sides. There's no loss of information. It's a completely unitary system if you take into account both the photons and the electrons. But now when you get to the Rindler Observer, you have a problem, because the Rindler Observer, both Simplicio and Sagaccio have exactly the same problem. Simplicio does not want to look at the photons, but Sagaccio cannot look at the photons because all the soft photons go into the region of space which is not accessible to the accelerated observer. Yeah? So in this system, there are actually horizons which are swallowing information. That's not true in the thermal situation that I was talking about. Now, probably one fine point is that I could have a Rindler observer who somewhere here decides to stop accelerating and crosses the horizon and collects all the information. I'll leave that for you to think about, but I noticed in one of Suvrat's papers, he talks about an observer who is out for a while and then jumps into the event horizon of a black hole. Many questions which are the black hole entropy also appear here. Yeah, perhaps. Yeah, I'll stop at this point.
Okay, so in these neutron experiments that were done, the neutrons were, one just did the two-slit experiment with neutrons in the gravitational field. And what was observed was you got the same pattern, but just shifted downwards because the neutrons were freely falling in the gravitational field.
Yes.
So in this case, we want to be in a strong gravitational field, but we want to prevent the neutrons from freely falling, because if they freely fall, then they won't see the temperature. So for that, we need to do something to make them interact with some other field, which maybe could be a waveguide or could be the electric field itself. And it worries me that would cause, because that's a strong interaction, because the acceleration is strong, that would cause these particles to get entangled with the external force that we are applying.
Yes.
And so that might just be a stronger effect than this effect.
Yeah.
This is related to the question I asked earlier, which is that, whatever you do in the accelerating frame to keep the electrons on track,
yes,
might itself lead to loss of coherence.
Actually, that's a good point, but let's look at this old question about whether an accelerated charge radiates or not. So if you take the inertial observer's point of view, so there's a charge accelerating like this, coming from minus infinity and going to plus infinity. An inertial observer can work out the Lienard-Weichert potentials of this. He gets field out here. Now, if you go to the rest frame of the Rindler observer, he also can do the same thing. What happens is that the electromagnetic field configuration that both work out is exactly the same. This guy sees Bremsstrahlung coming from this. The other guy sees nothing but a Coulomb field. That's possible to check. In fact, a simple argument gives that conclusion. If you go to this guy's frame, you find that Maxwell's equations are time reversal symmetric. And what you see is a static field there's no magnetic field in his frame. It's a pure electric field. So what he sees is a Coulomb field. So he will not see any Bremsstrahlung, this guy. He will say it's an electron at rest. That's completely consistent with the point of view of the inertial observer, because all the Bremsstrahlung which is emitted is actually going to places where this guy doesn't see it. Another point is that the division of radiation into Coulomb and transverse is actually frame dependent. So that's a deep point. So you can have perfect consistency between apparently differing points of view. So I'd like to make another point that, see, we are entering new territory here, and it's a good idea to not assume that the things we knew for sure are still true. For example, when we went to special relativity, the notion that time is a path function is a completely new notion. Earlier we thought that time was the same for everybody, but time actually depends on the observer. Here also, it's entirely possible that entropy will depend on the observer. Yeah? And for example, the notion of particle depends on the observer. It's also possible that the notion of entropy depends on the observer. And whether he's Simplicio or Sagaccio, he might see different kinds, he might have different ideas of what entropy is. Entropy may be something more subjective, depending on how you define it. For example, the observer who who cheats on the accelerated frame and jumps across the horizon, he will probably be able to see unitary evolution. But the other observer who's in the accelerated frame forever, he will see loss of information. Yeah, I don't know if this answers your question. Yes.
Some question, and it's the following, that, in string theory, for example, we have been able to understand black hole thermodynamics in a similar way, exactly the same way as in statistical mechanics.
Yes.
The idea of temperature, entropy, we understand in terms of coarse graining and all that.
Yes.
Now, regarding this Rindler Observer, is there such a elementary, simple description for me to be able to derive the temperature in terms of objects, actually?
In terms of degrees of freedom. In terms of degrees of freedom, yeah. Actually, I don't know. I think you would be much better placed to answer that question than...
So I asked a question, maybe others know here.
Yeah, maybe Subrat or...
We need an IR cutoff on the fun trimester. We need an IR cutoff to make you a finite entropy. The entropy is infinite.
I thought you need a UV cutoff, is it? No, IR, is it?
Also, there's just a lot of soft degrees of freedom. You're saying you also need but in any case, there's also an IR problem. But
yes.
There's also a UV problem. But so we need something to make the entropy finite.
No, but where is the stuff? I mean, in the sense that here I know the argument. I mean, for Rindler temperature. I mean, it's such a simple argument from general relativity that there is a temperature related to the acceleration at the horizon.
Degrees of freedom in the modes of the fields, right? You're just counting the degrees of freedom in the modes of the field. There's a mode of the field and a mode of the field. You're just counting that degree of freedom. The Rindler density matrix is just obtained by tracing out over the left half, but it's a pure field theoretic argument. So in the field theoretic argument, you would have to do something to put cutoffs to make it finite, but the answer you're getting is just by tracing over some of the modes of the field. So that's all there is in the universe.
Which field?
There is some scalar. There's some scalar field or
the
something. There's an electromagnetic field in this case.
Yes.
So you're just tracing over the other half. So there's no microscopic puzzle in a sense. You just get what you.
So what is the basis of the argument that if you are an accelerating observer, I'm just accelerating, then I will see a thermal bath.
It's this
Andrew effect.
I mean,
no?
and if I
think it was there in Subrat's talk also, where you have, in fact, what is it, a thermal double, right? I mean.
Yes. So in this case, you won't see the other half, right? If that red line can't see the other half, so that person traces over the things on the left. So you see a thermal bath.
Yeah, I understand all that, but still that doesn't somehow, maybe my question is framed not so well, perhaps, but...
Yeah.
You want a cutoff independent way of...
Yeah, just a counting, we did black hole entropy by counting. We did all that just by a counting argument of degrees of freedom.
You're puzzled why it's coming out so simply as the entropy of entanglement. You're saying it shouldn't be the entropy of entanglement, there should be something else.
So,
You're asking why is the answer so simple, in a sense. Why don't we?
it's simple because of rules of
Yes.
But the microscopic answer is also trivial.
No, perhaps we should postpone this because, in case next speaker. Yeah, I'm sorry.
I have suppose you wanted to do this experiment in reality.
Yes.
The accelerated...
Let's just switch it on.
The guy in the accelerated frame would see a very strong electric field, the Coulomb field that you were talking about.
No.
Would it be large?
No, yeah, that's right. So you have the whole apparatus in an accelerated frame of reference. That's what you're saying? Yeah.
And then from the perspective of the accelerated observer, the electric field would be
large, let's say.
Large.
Yeah, yes.
But then you would have showing a pair production, and would that affect your...
not that large. The accelerations have to be such that If the electric field is very large, it's true, there will be Schwinger pair production, and that's something I would like to avoid, That's true. I don't want to have such. So the laboratory chances are probably better with the first experiment, which itself has not been done. The second one is probably, if you want to do it in an experimental form, probably it's better to do analog gravity, where the speed of light is replaced by the speed of sound, and the accelerations can be much smaller. Yeah, actually, that's completely right. At the moment, what we have is a space for decoherence. That is to say, a spatial length. There's a size of the apparatus, d, and the decoherence occurs over space. But of course, and that comes because I'm doing a stationary experiment. But if I do a time-dependent experiment, that spatial distance will translate into a decoherence time.
Since you in the accelerated frame you can connect, you can get an effective temperature.
Yes.
You can basically use that to kind of compute a
computer time, right? Yeah. But in order to convert it into a time, I need to do experiments with more than one energy, not a monoenergetic beam, but two energies which will beat against each other and produce a time. Because in a monoenergetic beam, I'm doing equilibrium statistical mechanics, which is much easier than non-equilibrium. Yeah, that's right. So I only have a decoherence length, not a decoherence time, because there's no time in my problem. And that is deliberate to make the analysis simpler.
Will it depend on with which direction the acceleration is?
No. You could choose Z, X, or Y. It's equally good in all directions. No? Rindler Observer can be accelerating in any direction. I just chose Z along his direction of acceleration for convenience. I mean,
He's asking if the apparatus has to move in that direction or you're accelerating in this direction. If the apparatus
Exactly.
so, sorry, what is that?
There is a direction for acceleration. Why is the temperature isotropic? That's the question.
Oh, yeah. No, that comes from the Andrew effect. If you go to the frame of the observer, it's exactly like a thermal bath frame. The population of the oscillators is actually described by a density matrix, which is e to the minus beta h. That comes out of basically tracing over the left Rindler wedge. And I don't have time to explain it now, but I can talk to you later.
Just one more short comment. I think you're right that the electron won't radiate, but this accelerating observer will nevertheless have to apply a very strong electric field. Let me think of it that way rather than a waveguide, because it's simpler to.
Yeah.
Now, I think one thing one will have to ensure is that, so you're right, there's no radiation.
Yes.
Because this person sees different, but this electric field will have to be extremely homogeneous. Because the moment it's slightly inhomogeneous, you'll end up measuring the position of the electrons. So there'll have to be a very strong electric field.
No, suppose he
very
uses.
homogeneous between the two slits.
Suppose the accelerating guy uses a rocket ship to accelerate himself. No electromagnetic fields, right? And everything in the apparatus is transparent to radiation. Then
Everything in the apparatus, yes, but this accelerating observer is doing this two-slit experiment with electrons.
Yes.
But he wants to prevent the electrons from accelerating because of the pseudo force. So he applies the electric field to counteract that pseudo force.
No, he puts everything into tubes. Let's suppose you have tubes or something like that.
Tubes
Metals.
have to have some other interaction. So the tubes are a more complicated interaction between electrons and metals. So if you think of electric field, it may be simpler. You could just apply a homogeneous electric field,
Okay.
which would counteract the pseudo force.
Right.
But the homogeneous electric field would have to be really homogeneous, because if it was inhomogeneous, it would measure the position of the electron.
Yes,
And it would
yes.
then entangle the electron with the.
Okay.
So all I'm saying is that when you have very high accelerations, you'll also need very strong electric fields to keep the electron in place.
Yeah.
And they will have to be very homogeneous.
Okay, let's suppose that they are homogeneous.
Yeah, I think people should